Morning engineering class, how you guys doing? Today we're going to take a quick look at another aspect of kinematics that's pretty important, and that is we're going to apply kinematics to the concept of falling objects, and so we call that free fall. So today's topic is free fall, and as you can see we have our kinematic equations already there. So what are we going to do? Well, we're going to say we're going to try to understand how it is that we can use these four equations here to understand how falling objects move. And essentially, the reason that we can apply these four equations is because these four equations work for a particular circumstance, and that is constant acceleration, right? So I don't know if I can write that in here, but I'm going to try. Okay, so constant acceleration. That's very, very important. So what that means is, you step on the gas pedal of your car, and it's a nice smooth acceleration. You don't feel any jerking, no gear shifting, anything like that. So you're picking up speed at the same rate the whole time. So in any case, free fall happens to be a case of constant acceleration. In the case of free fall, the acceleration is the acceleration due to gravity, so we call it g, and it is 9.8 meters per second squared. And what that means is that for a falling object, as it falls, it will pick up speed at a rate of 9.8 meters per second for every 1 second that it falls. So if it's fallen for 1 second, it's moving at 9.8. If it's fallen for 2 seconds, it's moving at 19.6. If it's fallen for 3 seconds, it's moving at 29.4, and so forth. So with that said, 9.8 is about 10, so you can just think of adding 10 for every second that an object falls. About 10 after 1 second, 20 after 2, 30 after 3, 40 after 4, etc. So basically, falling objects pick up speed. All of them pick up speed at this rate. Now, it's first worth noting that this is kind of interesting in the sense that if you ask, the average person on the street, and you say, hey, if I drop this marble and this bowling ball at the same time, which one will hit the ground first? Most people think the bowling ball will hit the ground first. So you got this little marble, you got this big bowling ball, right? And you say, let's drop them, which hits the ground first? And the answer is actually surprising to a lot of people, and that is they both hit the ground at the same time, okay? So this is something that was discovered by Galileo back in the 1500s. It may have been unknown to other people, surely, but the problem was the conventional wisdom at the time was that heavier objects fell faster. You guys have probably heard of a philosopher by the name of Aristotle, and Aristotle thought that heavier objects fell faster than lighter objects. And this does make some sense. I mean, if you drop a heavy stone on your foot, it hurts. And if you drop a twig on your foot, it doesn't hurt. So one reasoning there is, well, if it's moving faster, it's going to hurt more. And so maybe that's where that came from. But in any case, it doesn't matter. It's just not true. And so you can do this experimentally. If you're feeling experimental today, I encourage you to try this out. What you could do is, take an object that you don't mind dropping, maybe a ball or something, and then a piece of paper, right? And leave the paper flat, and then drop the two at the same time, and you'll see the ball hits the ground first, right? On the other hand, you can then reconduct the experiment, and you notice that if you take that piece of paper and you crumple it up now into a ball and you drop it at the same time, even though the mass of the paper is the same, it falls faster and it falls about the same time as the ball. So basically, light things that do fall more slowly, they're only falling more slowly because of air resistance. And of course, in Aristotle's day, understanding exactly what air wasn't something that they did. They had no idea of atoms or molecules and all that stuff. They could only guess or have conjectures, and certainly they didn't have modern science, so we can understand why that mistake was made. But yeah, air resistance is definitely a part of it, and yeah, as soon as you eliminate air resistance from the equation, you don't have heavier objects falling faster anymore. So it doesn't matter. I mean, if you have a boulder and a penny, and you drop them from the same height at the same time, they'll hit the ground at the same time. It's a remarkable fact. It's how gravity works. So without getting too much into that, I want to just, I suppose, take a look at how we would apply these equations to free fall then. Okay, so I'm going to erase a bit here, and hopefully that's not an issue for you guys, because you can rewind on videos, so that's nice. And what I want to do is just point out a few things. First is, of course, just a reminder, as we said, A is now lowercase g, which is 9.8 meters per second squared. And it's worth noting that this is always a downward value. Now, when you solve a problem, whether you're really thinking about it or not, you are generally going to choose a coordinate system. And what that means is you have some idea of left and right or up and down in your mind. And you guys are used to this coordinate system from math class. This is called the Cartesian coordinate system. It's named after the guy who came up with it, Rene Descartes. So it's the Cartesian coordinate system. And we have here negative values on the left and negative values down, right? So that's what you're probably used to from math class, and that's perfectly fine. So what that means, though, is since our acceleration is down and down is negative, then we're probably going to typically use a downward negative value of g. But just keep in mind that there's nothing that stops you from having a positive down value for g, but then up is negative. So everything that is pointing upward would have to be negative. So if I threw a ball upward, its velocity in the beginning would have to be negative. That tends to be more confusing for students, so typically we just choose down to be negative. So with that in mind, just cleaning up a little bit here, what we're going to see is that we're going to go ahead and insert a negative sign in front of 9.8, and all that means is, again, anything that's down is negative. Now, that means velocities will be negative, so if an object is moving downward with a velocity v, if that v is 10, then we have to make that negative 10. And it also means that if an object falls downward a distance or a displacement of 10, then it falls negative 10 meters. So the displacement can be negative. And again, all that negative sign means is that the object has moved downward. So if the object is traveling downward, then its velocity is negative. If it has fallen downward, then its displacement is negative. And if it's speeding up in the downward direction, then its acceleration is negative, okay? So we just have to make sure that as we choose our coordinate system, we are consistent in that choice and we make everything that is supposed to be negative, negative. So we're going to generally stick with this coordinate system then, with positive being up and negative being down. And we're going to work within that coordinate system. Now, when it comes to solving problems with these equations, free fall problems, it's not too different than what you've already done with kinematics. So you're going to do the same process. And so this means that you're going to, write your given information. You're going to, choose your equation based off of what's missing, as you saw in a couple of my example problems, right? The hard part about free fall is really the fact that generally you're not given as much information. So you might read a problem and you'll say, well, how can I solve this? I only have like one piece of information. That's not nearly enough to be able to solve. And so I'm going to give you a few tips here to help you understand that there's more and you're probably just forgetting and going too quickly. So let me give you a few pointers. So the first thing is if an object is dropped or if the object falls, right? Then that tells you something about that object's initial state, and it tells you that the initial velocity is 0, okay? So if an object falls from rest, or is dropped, then the initial velocity is 0, and so I'll also put the words from rest in here, because you saw that more with like your kinematics. All of these are very important when it comes to identifying given information. So in other words, you might start a problem, you read the problem, right? And you're looking for numbers because your brain is always trying to do the shortcut. You always want the path of least resistance. Well, that's fine, but if you do that, you're going to probably miss the fact that it says, hey, from rest, or it was dropped, or the object fell. And those words are actually telling you numbers, so don't miss that. That's very important. So if an object is dropped, VI equals 0. The second thing to keep in mind is that, I'll just circle it right here, right? A is equal to G, which is equal to negative 9.8. So for every free fall problem on Earth, you already know acceleration, right? That is a ubiquitous, always given value. So you always know A is equal to negative 9.8 meters per second squared. So you'll make a list of variables, and if you make that list and you write your given information, Don't forget, if you're on planet Earth, then A is 9.8 meters per second squared. Now, yeah, I've said on planet Earth, so that means that if you're on Mars, the acceleration due to gravity is a different value. So on Mars, G is not 9.8, it's about 3.7, and on the Moon, it's about 1.6, and it has different values at different places in the universe, of course, if you're on a different planet. You can't really stand on Jupiter, but I believe it's something like 27 on the surface of Jupiter, but again, the surface is like, gas and clouds, so you can't stand on it. But if you could, you'd weigh about 3 times what you would have otherwise. So anyway, with that said, don't forget, as I said here, that your acceleration is always known and always given if you're in a free fall problem. Okay, and then, I guess the only other tip I would say is just remember, I'll give you sort of a don't do this part. On these problems, when they ask you about the final velocity, it's very tempting for you to say, well, this object fell, so it's going to hit the ground and it's going to be moving at 0. No, actually, we're always concerned about the final velocity just before it hits the ground. And there's a couple reasons for this. Kinematics, remember, we can only use kinematics to understand motion with constant acceleration, which is, right there. So if it doesn't have constant acceleration, you can't use kinematics anymore. Now, why would hitting the ground mean not constant acceleration? Well, because when it is falling, it's speeding up downward due to gravity, 9.8, and when it hits the ground, it's going to speed up upward. In other words, it's going to slow down. So you have a different acceleration when you hit the ground than you do while you're falling, and therefore you can't use kinematics. So we stop our analysis to get around this problem. We stop our analysis at just before it hits the ground, and then that allows us to use these kinematic equations still. So if you're thinking in your mind, oh, this object falls and hits the ground, so VF equals 0, no, you are incorrecto. It is definitely not final velocity 0, so that's very important. And yeah, don't forget that if it's falling downward, your displacement, you can call it delta x, you can call it delta y, but that's going to be a negative value if it's falling, okay? So now, can I have a problem with free fall where the object is rising? Sure, it's called throwing a ball upward, right? But just be aware that if you know it's falling downward, then when you write your delta x, then you want to make sure that delta x is in fact a negative value. So don't forget that, that's very important, okay? All right, so I've talked enough. We're going to go ahead and do a quick example problem, and then my wife and I are going to go get Animal Crossing from Best Buy because she is dying to get it. Don't worry, we're going to wash our hands and keep our social distances. Okay, so example problem real quick. Here we go. So we got a squirrel that falls out of a 5-meter high tree. It started from rest, and we need to determine the time of the squirrel's fall and the final speed of the squirrel just before it hits the ground. What a derpy squirrel, man. Falling out of a tree. It's got to be embarrassing. All right, so let's go ahead and solve this problem. We're going to start with part A here to find the time of the squirrel's fall. Okay, so part A. So what I recommend is just making a list of information, right? And actually just write this every time, okay? If you haven't already been doing this, I just like to make this list right at the get-go so I don't forget anything, right? So you just get used to making this list. All right, so the squirrel falls out of a 5-meter high tree. So what does that tell us? Well, it tells us the height of the tree, and we know it was 5 meters. But, oh shucks, I made a mistake. Mr. Johnston, weren't you paying attention in the lecture? You know that you're supposed to make sure that if an object falls, its displacement is negative, right? So there we go, negative. So negative displacement. Okay, cool. So don't forget that the displacement is downward negative. Okay, cool. What other information is given in the problem? Well, that's the only number. I guess that's all I'm given. No other details or, oh wait, from rest. Yeah, see that right there? Let me make sure that's circled. Nice and circled there. Yeah, okay, anyway. So it's from rest, so what does that tell us? Well, of course it tells us that our initial velocity is 0. Booyah. Very important information. And then finally, well, what do I mean? There's nothing else. There's only 2 pieces given information. I need 3 to solve. I can't solve this problem. What planet am I on? Oh yeah, Earth. Cool. Sorry, I've had my caffeine today. All right, so now that I remember that the displacement is -5, the initial velocity is 0, and the acceleration for a squirrel on Earth would be -9.8 meters per second squared, just like everything else on Earth, then I can go ahead and solve. And what do they want? They want to know the time of the squirrel's fall. Whoops, not that. They want to know the time. So for part A, I'm going to solve this by looking for the equation that does not have final velocity, okay? Because whichever equation does not have final velocity will relate the other 4 variables that I need. So I'm going to go ahead and look up here, looking for an equation without VF, looking for an equation without VF. Equation 1, VF. Equation 2, VF. Equation 3, sweet, no VF in equation 3, so I'm going to choose equation 3 for this problem, okay? So we're going to go down here. We're going to write equation 3, which is delta x equals vi delta t plus 1/2 acceleration times squared. Cool. And then we're going to plug into our numbers here. -5 equals vi, which is 0 times delta t. Hey guys, what's 0 times delta t again? I can't remember. Oh yeah, it's 0. Don't make that silly mistake. Of course it's 0. Everything times 0 is 0. And look at that. Now I have my delta t and I can solve. How do I solve this? Well, I'm going to multiply. You can do this however you want. I'm just showing you how I would do it. Multiply both sides by 2. Because algebra, I'm allowed to do that, right? Divide both sides by -9.8. Booyah. Okay. And then I'm going to go ahead and get a number here. So this is almost 1 on the left side. 10 divided by 9.8 gets me 1.02. Oopsie. 1.02 equals delta t. And so I'm going to take the root of the square, and I'm going to get 1.01 seconds. Yeah. So if this squirrel falls from 5 meters high, it's going to hit the ground and say ouch about 1.01 seconds later. I think it'd be pretty funny to see a squirrel say ouch. Maybe to hear it even. All right. Part B. Find the final speed. Let's get that out of the way. Let's find the final speed of the squirrel just before hitting the ground. That's what part B wants to know. Final speed, well, I guess I'm looking for VF, okay? Now, I'm going to go back up to my list here. I'm looking for VF, right? So my question has shifted from time to final velocity. So here my time I know is 1.01 seconds, and now I'm looking for VF. So how do I choose my equation? Well, you notice here we now have 4 pieces of given information, so you get to pick whichever of the 4 equations you want as long as it has time in it. So the only equation you're not allowed to pick here is the bottom equation. The bottom equation does not have time in it, so it's completely useless for us right now. So which of the 3 equations right here, which of these 3 that oh God, what did I do? Which of those 3 equations do you think is going to be more useful, or I'd say easiest to solve? I would say equation 2 is probably the easiest one to solve. But if you want to use equation 1 or equation 3, you can. It'll just be maybe a little bit trickier on the algebra front. But I'm going to do equation 2 because I'm lazy. Here we go. Equation 2, VF equals VI plus A delta T, initial velocity, oh yeah, that was 0, plus -9.8 times 1.01. Oh yeah, now we're going to know the final velocity of the squirrel right before it hit the ground. I'm going to guess it's going to be close to 9.8. What do you guys think? Oh yeah, 9.898. Let's go ahead and round that up to 9.9 meters per second. So that squirrel hits the ground at 22 miles per hour, guys. Let's just say I hope he hit the grass, because otherwise that is a new kind of roadkill. All right, well, there we go. I hope you guys, bless you, I hope you guys enjoyed our little lesson here. This is a nice example problem. You guys are going to have to do obviously a couple quick problems like this today. Good news, I'm not giving you any homework over break, of course, so I want you guys to really enjoy your time off, and I look forward to working with you when we get back from break, meaning back online. So take care, be safe, guys.